Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into the data warehouse, the system that powers every analytics dashboard, BI tool, and data-driven decision at scale. We'll cover how companies like Amazon, Netflix, and Snowflake store petabytes of historical data, serve sub-second analytical queries, and support hundreds of concurrent analysts. Whether you're preparing for a senior engineering interview or designing data infrastructure for your organization, this one is for you. Let's get into it. Welcome to Cloud Wizard. In this video, we are doing a complete deep dive into the data warehouse, the system that sits at the heart of every modern analytics stack, enabling business intelligence, executive dashboards, and data-driven decisions at massive scale. If you have ever wondered how companies like Amazon, Netflix, Airbnb, or Snowflake store petabytes of historical data, serve sub-second analytical queries, and power hundreds of concurrent BI tools, this video is for you. We will walk through the functional requirements, non-functional requirements, high-level system architecture, end-to-end user journey, core models, low-level design, and the key trade-offs that come up in a senior system design interview. Whether you are preparing for a FANG interview or designing data infrastructure for your organization, let's get into it. Here is the core problem. A company generates data from dozens of transactional systems, relational databases, event streams, third-party APIs, log files, and mobile apps. The business wants to answer questions like, what was our revenue by product category across every region last quarter? How did user retention trend month over month for the past 2 years? Which marketing channel drove the highest lifetime value customers? But OLTP databases are optimized for writes and row-level lookups, not for scanning billions of rows and aggregating across multiple dimensions. Running heavy analytical queries against production databases slows them down and risks data corruption. The business needs a dedicated system that ingests data from all sources, stores it in a format optimized for analytical reads, and serves fast, consistent, multi-dimensional queries at scale. That system is the data warehouse. Let's walk through the functional requirements. First, the warehouse must ingest data from heterogeneous sources including relational databases via change data capture, streaming systems like Kafka, flat file uploads, and third-party connectors, with support for both batch and near real-time ingestion. Second, it must apply transformations during or after ingestion, cleaning, deduplication, schema normalization, and business logic, so data is query-ready. Third, it must organize data into a dimensional model, most commonly a star schema with fact tables and dimension tables, supporting efficient multi-dimensional analysis. Fourth, it must support OLAP queries, aggregations, group by operations, time series slices, and drill down across hierarchies, while serving dozens to hundreds of concurrent analytical users. Fifth, it must expose a SQL interface and integrate with BI tools like Tableau, Looker, and Power BI, as well as support scheduled and ad hoc query patterns. These 5 capabilities define what a production data warehouse must deliver. Now the non-functional requirements. Query latency is paramount. Business users expect dashboard queries to complete in under 5 seconds and complex analytical queries in under 30 seconds, even over billions of rows. The system must scale storage independently of compute, since historical data grows without bound but query load varies. Throughput must support hundreds of concurrent queries without degradation. Data freshness matters for near real-time use cases. The warehouse must reflect source changes within minutes. For batch use cases, nightly loads are acceptable. The system must be highly available, with no single point of failure, since business operations depend on dashboard access around the clock. Data consistency and correctness are non-negotiable. Wrong numbers in a BI dashboard cost real money. And finally, the system must be cost-efficient, since storing and querying petabytes of data is expensive, making compression, partitioning, and tiered storage critical levers. Here is the high-level system architecture. On the left, source systems feed data into the ingestion layer through 3 paths. Batch ETL jobs using tools like Apache Spark or dbt pull snapshots from OLTP databases on a schedule, A change data capture stream using Debezium or Kafka Connect captures row-level changes in near real time. And a landing zone on cloud object storage like S3 or GCS receives raw files. The ingestion layer writes raw data into a staging area. A transformation layer applies business logic, runs data quality checks, and writes clean, modeled data into the core warehouse storage layer, which uses a columnar format such as Parquet or ORC, organized into fact and dimension tables. A query engine layer, Redshift, BigQuery, Snowflake, or Trino, executes SQL queries against the storage. A metadata and catalog service tracks schemas, lineage, and statistics. BI tools and analysts connect through a SQL gateway. The key metrics to memorize cold. Query P50 latency, which should be under 2 seconds for dashboard queries, and P99 latency, which should be under 30 seconds for heavy analytical workloads. ETL pipeline lag, the time from a source event to it being queryable in the warehouse. Target under 15 minutes for near real-time, and under 24 hours for batch. Data freshness percentage, the fraction of fact table partitions that are within their SLA freshness window. Storage compression ratio, typically 3 to 10 times for columnar formats, which directly reduces cost. Concurrent query throughput, measured in queries per second with acceptable latency. Query scan efficiency, measured as the fraction of data skipped by partition pruning and predicate pushdown, which should exceed 80% on well-partitioned tables. And pipeline error rate, which must be near zero since a failed load silently corrupts downstream dashboards. Let's trace the end-to-end user journey. A data engineer at a retail company configures a nightly ETL job that extracts yesterday's transactions from the OLTP database, joins with customer and product dimension tables, computes net revenue and return rate, and loads the results into a fact_sales partition in the warehouse, keyed by date. A business analyst opens Tableau the next morning, connects to the warehouse via the SQL gateway, and builds a revenue by region dashboard. The query hits the metadata catalog to resolve the table schema. The query engine prunes all partitions except the last 90 days, scans only the revenue and region columns from the columnar files, aggregates in parallel across the compute cluster, and returns results in under 3 seconds. The analyst adds a filter for a specific product category. The warehouse re-executes with additional predicate pushdown, and results arrive in under 1 second thanks to result caching. The analyst publishes the dashboard and schedules a daily refresh. The core models and algorithms. The star schema is the foundational data model. A central fact table records measurable events like sales or clicks, with foreign keys into dimension tables that describe who, what, when, and where. Slowly changing dimensions handle dimension updates. Type 1 overwrites. Type 2 adds a new row with effective dates to preserve history. ETL orchestration uses a directed acyclic graph of tasks, extract, validate, transform, load, with dependency tracking and retry logic. Columnar storage organizes data by column rather than row, enabling the query engine to read only the columns needed and apply vectorized operations. Partition pruning skips entire data files based on partition key filters, reducing scan volume dramatically. Run length encoding and dictionary encoding compress repeated values in columnar data. OLAP cubes and materialized views pre-aggregate common query patterns to serve sub-second latency without full table scans. The key trade-off is normalization versus denormalization. More joins are slower but save storage, while flat wide tables are faster but redundant. Now the low-level design deep dive. The fact table schema includes a surrogate key, a date partition key, foreign keys to each dimension, and additive measures like revenue, quantity, and duration stored as fixed precision numerics. Partition strategy is critical. Partition by date on most fact tables, with subpartitions by region or business unit for high cardinality tables. Each partition is stored as one or more Parquet files in object storage, with row group statistics, min, max, null count, written into the Parquet footer, enabling the query engine to skip row groups without reading them. The ETL pipeline writes to a staging table first, runs data quality assertions, null checks, range checks, referential integrity, and promotes to the production partition only on success. Idempotency is guaranteed by using upsert logic keyed on the surrogate key. The metadata catalog stores table schemas, partition manifests, column statistics, and data lineage in a relational store, queried by the planner before execution. Query routing sends short queries to a small compute cluster and long-running queries to a large dedicated cluster to prevent resource starvation. Key takeaways for your interview. First, a data warehouse is an OLAP system optimized for read-heavy analytical queries over historical data, fundamentally different from OLTP systems, so always lead with this distinction. Second, the star schema with fact and dimension tables is the canonical data model. Know it cold, including slowly changing dimensions. Third, columnar storage, partition pruning, and predicate pushdown are the three pillars of query performance. Explain all three and their interaction. Fourth, ETL pipeline reliability is as important as query speed, mention idempotency, data quality assertions, and staging before promotion as key reliability patterns. Fifth, the hardest design challenge is balancing freshness against cost. Near real-time ingestion requires streaming infrastructure and micro-batch loads, while nightly batch is cheaper but stale. If you can articulate these 5 points with confidence, you will demonstrate senior-level data systems thinking. That's it for the data warehouse. If this helped, like and subscribe, and I'll see you in the next one at Cloud Wizard. And that's a wrap on the data warehouse. We covered the full picture from multi-source ETL ingestion and star schema modeling, through columnar storage, partition pruning, OLAP query engines, and the low-level design of fact tables, ETL DAGs, and metadata catalogs. If this video helped you, please hit that subscribe button and the bell icon so you never miss a new system design video. Drop your questions in the comments below. I read every single one. See you in the next one at Cloud Wizard.